Bismillahirrahmanirrahim. Let's take up the next problem, which is 3-30 of our book. Although it seems a little bit lengthy, but it is very important and interesting problem. However, it is not difficult at all. It says that the performance of gas turbine engines may be improved by increasing the tolerance of the turbine blades to hot gases emerging from the combustor. So they are talking about the increasing the tolerance of the turbine blades, tolerance against the hot gases that are coming out of the combustor or combustion chamber of the gas turbine. So the hot gases would come out of the combustion chamber and they will then enter the turbine. So the turbine blades would be facing the highest temperature combustion gases. One approach to achieving high operating temperatures involves application of a thermal barrier coating TBC to the exterior surface of the blade. So one of the approaches is that they coat the outer surface of the turbine blade with this thermal barrier coating TBC. So now the turbine blade will not face the combustion gases, rather it is the thermal barrier coating TBC that will face the hot combustion gases, while passing cooling air through the turbine blade. So they do not only coat the outer surface with the TBC, but they also pass the cooling air through the turbine blade. If you Google it out, you will probably see some images in which you will see the micro holes drilled in the turbine blades, and that is that passage that they are talking about for the air to pass through, for the cooling of the inside of the blade. Typically the blade is made from a high temperature superalloy such as Inconel, K of which is 25. So they are taking an example in which the turbine blade is made of a superalloy. It's Inconel, K of which is 25 watts per meter Kelvin, while a ceramic such as zirconia, K of which is 1.3, is used as thermal barrier coating. So the turbine blade is made of Inconel having thermal conductivity of 25, whereas zirconia, which is a ceramic, is being used as TBC, K of which is 1.3. Now consider conditions for which the hot gas is at 1700 Kelvin. So the temperature of the gases leaving combustion chamber and entering the turbine is 1700 Kelvin, and cooling air at 400 Kelvin. T infinity I is 400 Kelvin. So cooling air is at 400 Kelvin. Now you may think that what type of cooling air is that, which is at a temperature of 123 degrees Celsius. In fact, the temperature at both sides of the turbine should have a suitable temperature gradient, should have a suitable temperature difference. Otherwise, thermal shock phenomena may happen in the presence of very large temperature differences. So anyhow, the gases are at a temperature of 1700 Kelvin, and the cooling air which is being passed through the inside of the turbine blade is at 400 Kelvin, and they provide inner and outer surface convection coefficients of 1000 and 500 respectively. So convection coefficient on the outer surface of the turbine blade is 1000, whereas convection coefficient on the inner surface of the turbine blade is 500. Now if a 0.5 mm thick zirconia TBC is attached to a 5 mm thick Inconel blade, so we are given the thicknesses of the TBC and the turbine blade material Inconel by means of a metallic bonding agent, which provides an interfacial thermal resistance of 10 to the power minus 4. Now what is this metallic bonding agent? See, it's like some sort of, you can say, glue. If you want to paste two surfaces, you need to put a sticking agent, a bonding agent between those two surfaces. The similar thing is being explained over here. Means that if we want to put the thermal barrier coating, if we want to paste the thermal barrier coating on on inconel, which is the turbine billet material. So that is accomplished by using some sort of a bonding agent, some sort of a glue. I shouldn't say glue, but you should understand what I am trying to make you understand. It's a bonding agent, right? So that bonding agent will be between the turbine blade material inconel and the TBC, and it will stick the two surfaces together. It will join the two surfaces together. So that is the interfacial thermal resistance. So wherever there is a material, it will offer some resistance, large or small. So of course turbine blade material would have its own conductive resistance, and the thermal barrier coating will also have its own conductive resistance, thermal conductive resistance. But this material which is in between the two, which is in between the TBC and the turbine blade material, so this material, since it is a material, so it will also offer some resistance, some thermal resistance, which is being called interfacial thermal resistance, the value of which is 10 to the power minus 4. You will see that it is being represented by R double dash TC. So T would probably be referring to thermal, and C would probably be referring to conductive or a conductive, right? And then it says double dash. Double dash means it would be the resistance per unit of area. So therefore the units are not Kelvin per watt, because Q is delta T over resistance. So resistance is delta T over Q, means Kelvin per watt. But the units are not Kelvin per watt only, rather it is being multiplied by meter square. So I had explained in the earlier slides that the units of resistance are Kelvin per watt, and if it is resistance per unit area, then it would be meter square Kelvin per watt. And over there I also had explained that why meter square or the area goes into the numerator. So if those conditions exist, we need to find out whether the inconel, means the turbine billet material, can be maintained at a temperature which is below its maximum allowable value of 1250 Kelvin. So we need to make sure, or we need to find out whether under those circumstances, under all those conditions and thicknesses and temperatures and convection coefficients, is the inconel being maintained at a temperature below 1250 Kelvin, which is the allowable temperature for inconel, for this superalloy. Radiation effects may be neglected and the turbine blade may be approximated as a plane wall. Over here you can see the figure that this is the turbine wall. Outside is TBC and inside is the inconel, and between the inconel and TBC we have this metallic bonding agent. So there would be a conductive resistance associated with the inconel, there would be a conductive resistance associated with the metallic bonding agent, and there would be a conductive resistance associated with the thermal barrier coating. Now hot gases, or rather the TBC is facing the hot gases. So between the hot gases and the thermal barrier coating there would be convection, and associated with that convection there would be a convective resistance which would be given as 1 over HA or 1 over H naught A. And similarly inside the cooling air is being passed through. So between the turbine blade material, which is inconel, and the cooling air inside, there is convection taking place. So therefore there would be associated to which there would be convective resistance, which would again be 1 over HA or specifically 1 over HIA. Similarly, the conductive resistances which are being offered by the bonding agent and the turbine blade material and TBC, since they all are conductive in nature, and we are being told to approximate the turbine blade as a plane wall, means we need to deal this problem in Cartesian coordinate system. Therefore the resistances, those three conductive resistances would be L over Ka or delta X over Ka, where L or delta X would be the thicknesses of the turbine blade material, of the bonding agent and of TBC, and K is the conductivity of each of those three materials. This R double dash TC is telling us that we would be dealing the things in per unit of area. Otherwise they would have given us the total resistance instead of resistance per unit area. This is an indication that we would be doing the things in per unit of area. Now If you take a look over here, this is the same diagram, and this is the TBC, and this is the Inconel, and they are being joined together with a metallic bonding agent, and that metallic bonding agent is providing a resistance per unit area of 10 to the power minus 4. So now we have got 5 resistances. 3 are conductive in nature, as I just told you, and 2 are convective in nature. So 1 over H naught A, L over Ka due to zirconia or TBC or ceramic, whatever you like to call it, and then this one is the metallic bonding agent interfacial resistance, and then this resistance is due to the turbine blade material Inconel itself, that is why it says IN or INC, and then we have got this convective resistance which would be given as 1 over HIA. Kindly note that all the resistances are written on per unit area basis, so that is why this is R double dash TC, and we do not see area in any of the denominators of L over K or 1 over H. Okay, so all the resistances are on per unit area basis. Now if we look over here, this T infinity naught is at the highest temperature, of 1700 Kelvin, and this is at the lowest temperature of 400 Kelvin. So this would be the direction of heat flow. Now what we need to find out? We have to find out whether the Inconel, so where is Inconel? This is Inconel, right? Whether the Inconel would be maintained at a temperature below 1250, which is the allowable value of the temperature. Now over here, if across Inconel we call the two temperatures as Ts naught and Tsi on the outer surface of Inconel and on the inner surface of Inconel, or you may call them T1 or T2, it does not matter. Now out of Ts naught and Tsi, we need to find out, we need to make sure whether Ts naught and Tsi would be less than that particular temperature value, 1270 Kelvin. Now 1250 Kelvin. So even out of these two, we only need to find out Ts naught. We do not need to find out Tsi. Why? Because Tsi would be less than Ts naught, because this is the direction of heat flow, and heat flows in the direction of decreasing temperature. So if Ts naught is greater than 1250, the design will not be safe. And if Ts naught is greater than 1250, then the design will not be safe. And if Ts naught is less than 1250, then Tsi would be even lesser. So even out of these two, we need to find out Ts naught. So this problem is a very simple problem. All we need to do is find out this temperature. And from the past problems, we have learned that if we are to find out the temperature, we must know Q. So can we find out Q? Again, Q will be found out using the known temperature difference. So what temperatures do we know? T infinity naught, 1700 Kelvin, and T infinity I, which is 400 Kelvin. So if we write Q as delta T over R over resistance, and if we write delta T as T infinity naught minus T infinity I, then what we will write in the denominator? We will write all the resistances that fall in between these two temperatures. And how many are there? All 5. So all 5 resistances will go into the denominator. So all 5 resistances will go into the denominator. And then we would be writing all the resistances on a unit area basis, where area will be taken out and then it will be taken into the numerator, and then it will be taken into the denominator of Q, and we would be dealing in terms of heat flux. Since we know all the values, we know H naught, we are given H naught as 1000, we are given Hi as 500, and we are given the thicknesses of TBC and Inconel, and we are also given the value of the thermal conductivity of TBC and Inconel as well. So all we need to do is just put the values, and we will get the heat flux as 3.5 exponent 5 watts per square meter. Now what we need to do is write Q as delta T over resistances including Ts naught, because this is the temperature that needs to be found out. Now we can write Q as, for example, T infinity naught minus Ts naught. Then we would be having 3 resistances in the denominator. Or we can write Q as Ts naught minus T infinity I. Then we would be writing 2 resistances in the denominator. So this is a shorter route. But even then, this would give you the same answer, right? But it involves 2 terms in the denominator, whereas this involves 3 terms in the denominator. So we write Ts naught minus T infinity I over these 2 resistances. One is the resistance of Inconel turbine billet material, and one is 1 over HIA. So we know the thicknesses and we know the conductivities. So we calculate Ts naught as 1174. It means that the temperature of Inconel will go up to maximum of 1174. Tsi will be even less than 1174 Kelvin. So the design is safe. So you would have seen that how useful that example was. You came to know the turbine billet material. You came to know that turbine billet materials are even coated with a thermal barrier coating, which would be a ceramic having a very low thermal conductivity, and there is a passage for air to flow inside the turbine blades. So it was a very informative problem in that sense. Let's take the next problem, which is 348 of our book. It says a thin electrical heater. A thin electrical heater. See, as soon as you see the word thin, that probably would be an indication that you would be neglecting the resistance of that particular material. So a thin electrical heater is wrapped around the outer surface of a long cylindrical tube. So we would be dealing in case of cylindrical coordinates. So there is a long cylindrical tube whose inner surface is maintained at a temperature of 5 degrees Celsius. So the inner surface of the cylindrical tube is being maintained at a temperature of 5 degrees Celsius. So if this is that tube, the inner surface is at 5 degrees Celsius. The tube wall has inner and outer radii of 25 and 75 mm respectively. So the inner radius is 25 mm, whereas the outer radius of this tube wall is 75 mm. And this tube wall has a thermal conductivity of 10 watts per meter Kelvin. The thermal contact resistance between the heater and the outer surface of the tube per unit length of the tube is R-Tc is equal to 0.01 meter Kelvin per watt. So this sentence requires a little bit of discussion. First of all, it says the thermal contact resistance. So we need to know what is contact resistance. And this contact resistance is between the heater and the outer surface of the tube, outer surface of the pipe. So over here what is happening is that the electrical heater is wrapped over the outer surface of the tube, of that cylindrical tube. So it is not the conductive resistance of the pipe. This value of 0.01 is not the conductive resistance of pipe, and it is nor it is the conductive resistance of the pipe, neither it is the conductive resistance of the pipe, nor it is the conductive resistance of the heater. Rather, it is the contact resistance between. You see over here the word between. It is between the heater and the outer surface of the tube. So there is some material between the heater and the tube. Now, if you join two materials, see, if you have a material such as glass, so we know that any material, whether it is glass or wood or steel or any other material, it cannot be made frictionless. Any surface cannot be made frictionless. Means there would be some oppressions and depressions if you take a look microscopically. And what happens is that when, for example, if we have two surfaces, and if we put those two surfaces on each other, then if we try to slide one surface over the other, it requires some force. And why is that force required? We require that force to overcome friction. We require that force to overcome friction so that one surface may slide over the other surface. Now, what happens is that the oppressions of one surface go into the depressions of the other and vice versa, and therefore the two surfaces get locked. The two surfaces get locked, and which causes friction, and we need that minimum force to overcome friction. Now, when we say oppressions and depressions means what would there be in the depression? Nothing. Nothing means there would be air in it. If there is a void surface, if there is an empty surface, what would there be? There would be air in it. And air is a material. And wherever there is material, it will offer resistance. Small or large, that would depend upon its conductivity. Now, what do you think of air? Is air a conductor or is air an insulator? Air is in fact an insulator because it has got very low value of thermal conductivity. So that air which will get trapped between the mating surface of the two objects, between the common surfaces of the two objects, would have air over there, and that air would offer resistance to heat flow. That resistance is called contact resistance, which would be at the contact surfaces of the two materials. That resistance is called contact resistance, and that resistance has a value of 0.01. The units are meter Kelvin per watt, and it is R-Tc. So R would be used for resistance, T would be thermal, and over here C may be conductive or it may be contact, right? That is not any problem. R dash will refer to this single dash will refer to resistance per unit length. So over here we are being told with this R dash that it would be resistance per unit length. Over here it is written in words that it is resistance per unit length, and suppose they do not write it and they do not write R dash as well. So how would we come to know whether it is total resistance or resistance per unit length or resistance per unit area? We will find with the help of the units. Again, the units of resistance are Kelvin per watt, and if it is being multiplied by area, it would be resistance per unit area, and if Kelvin per watt are being multiplied by length, so it would be resistance per unit of length. Now then it says the outer surface of the heater is exposed to a fluid which is at a temperature of -10 degrees Celsius, and the convection coefficient is given to us as 100 watts per meter square Kelvin. Determine the heater power per unit length of the tube. Where is this heater power coming from? Due to that heater, right? It is the heater through which the current will flow, and that current flow will cause the heat to dissipate. So we have to find out that heater power required to maintain the heater at 25 degrees Celsius. Whole heater at 25 degrees Celsius. Now, see, if we are told that the heater is thin, that is one indication that we would be neglecting the heater resistance, because it says it is thin. Number two, see, if it is thin, see how do we express the, kindly listen carefully, that how do we express the conductive resistance of any material in cylindrical coordinates? We represent it using log of R0 over Ri divided by 2 pi KL, right? So if it is very thin, so for the case of heater, its outer radius would almost be the same as inner radius. So it would be log of 1 point something, means log of approximately 1. And what is the log of approximately 1? It is approximately 0. Right? So it is not an assumption. All the things are taking us towards neglecting that resistance of the thin electrical heater. And lastly, see what it says in the last sentence. Determine the heater power per unit length of the tube required to maintain the heater at 25 degrees Celsius. Which surface? Because heater has got two surfaces, one inner surface of the heater and one outer surface of the heater. So if the whole heater is at the same temperature, means if at two nodes the temperature is 25 degrees Celsius, what can you say about its resistance? How can the temperature at the two nodes be the same? It can only be the same if the resistance is negligible. We have discussed it in one of the previous problems. So not only we are being told to neglect the resistance in the first sentence, we are also being told to neglect the resistance of the electrical heater in the last sentence, because we are being told that the whole heater is at the same temperature of 25 degrees Celsius. Now when the temperature at the inner and outer surface both are the same, it means that the resistance of the heater is negligibly small. So starting with the problem, how many resistances would there be? See, there would be a convective resistance between the inner fluid which is flowing through this pipe and the inner surface of the pipe. We are calling it R1, and that would be 1 over HA or 1 over HIA. Kindly note that we are not given HI, and we do not have any table for H because it is not a materials property. Then the heat will flow through this thickness of the steel, right? And this would be log of outer radius of the steel over inner radius of the steel divided by 2 pi KL, and this would be conductive, of course. Then there would be the contact resistance, which would be R3. We are given its value as 0.01 per unit length, and then the heat will reach to and then we will see electrical heater, because between electrical heater and the tube is contact resistance. So now the electrical heater will come into play, and its resistance would be R4. R3 is the contact resistance. R2 is the resistance due to the pipe material itself, tube material itself, and R1 is the convective resistance between the inner fluid and the inner surface of the pipe tube. This R4 would again be log of R0 over Ri divided by 2 pi KL, but as discussed, we would be neglecting it. And then between the outer surface of the pipe or electrical heater and the outer fluid, there would be convection, associated with which there would be convective resistance R5, which would again be 1 over HA. Right? Now, we do not have any information on R1 because we do not know the value of HI. So what we will do is that we will start our analysis. What we will do is that we will start our analysis from this point and not from this point. See, we can start our analysis from any point. Since we are not given T infinity I, so we would not be able to start our analysis or consider R1 in our analysis. We would not be able to do that. Now, this over here, the temperature is given to us as 5 degrees Celsius. Over here the temperature would be 25 degrees Celsius, right? Similarly, this R5 over here, T infinity outside would be minus 10 degrees Celsius, and we are given H0 as 100. So out of these 5 resistances, we will reduce our network to only 3 resistances. One, the resistance due to the pipe material itself. The second one, contact resistance, and the third one, 1 over HA, the convective resistance. We are not including R1 because we do not have any information about it. or R1 may be negligible as well if HI has a very high value, right? It may be negligible, but since we do not have any information, we are just starting our analysis from this point, Ti 5 degrees Celsius. And what is R4? R4 is in fact the resistance due to the heater. So these two nodes will be joined into one point, which would be the point of heat input, So our thermal network will now consist of 3 resistances. Now what is the temperature over here? 5. What is the temperature over here? 25. And what is the temperature over here? Minus 10. So we have got these 3 values of temperatures. So heat will flow from higher temperature to lower temperature. So it will flow from 25 to 5 and from 25 to minus 10. From higher temperature, what is the highest temperature? It is 25. Can the heat flow from 5 to 25? No. So this will not be the direction of heat flow. Heat will flow from higher temperature to lower temperature. So it will flow from 25 to 5 and from 25 to minus 10. See, it cannot flow from 5 to minus 10. Why? Because we have got a higher temperature in between the two. So if we call this Q1 and if we call this Q2, where are Q1 and Q2 coming from? It is this heat which is being supplied, which has maintained the temperatures of 5 and 25 degrees Celsius. Minus 10 is outside temperature. So if we call this as Q1 and if we call this as Q2, so this Q which is being supplied is being divided into 2. Q1 and Q2 is being divided into 2, which is Q1 and Q2. Now Q1 is flowing from T0 to this node and then to this node. So again, if we write this Q1 as delta T over resistance, so if we write it as 25 minus 5 means T0 minus Ti. So what we will have in the denominator? The two resistances, R dash Tc and log of outer radius over inner radius divided by 2 pi KL. And this Q, which is Q2, which is being written over here, so it would be T0 minus T infinity over 1 over HA, over 1 over H naught A. So now what we will do is that we will write this area as 2 pi RL because it is in cylindrical coordinates. So the heat would be coming out or going in, or it would be flowing radially. So it would be 2 pi RL. So we will write this area as 2 pi RL and R would be R3. So what is R1? R1 is the inner radius of the pipe. R2 is the outer radius of the pipe. And what is R3? R3 is the outer radius of the heater. But we are saying that this R3 is the same as R2. Why? Because the heater is thin. So in fact it would be R3, but that R3 can then be written as R2 if the heater is thin heater. So the outer radius of the heater would be the same as would almost be the same as the inner radius of the heater. Kindly note that we are not saying that the radius of the heater is 0. No, we are not saying that. We are saying that the outer radius of the heater would be greater than 75 millimeter. What is the inner radius of the heater? 75. So what would be the outer radius? It may be 75.001 millimeter or 75.1 millimeter. So outer radius R3 is almost the same as R2, inner radius of the heater. Now we will take the length common out and then it will go into the denominator of Q and we would be calculating the heat transfer per unit length. So it will become log of R2 over R1 divided by 2 pi K without L, and similarly this would be H naught times area 2 pi RL, where we will write it without the length. So we know all the values, so if you just put the values we get this Q dash as 2377 watts per meter. Okay, the next problem, which is 3-51, says that superheated steam at 575 degrees Celsius is routed from a boiler to the turbine of an electrical power plant through steel tubes, and the conductivity of steel tubes is 35. So we have got superheated steam at 575 degrees Celsius. It is being generated in the boiler, and then it is being routed from the boiler to the turbine through steel tubes, and the conductivity of the steel tubes is given. The steel tubes have 300 mm inner dia and 30 mm wall thickness. So the outer diameter would be inner radius would be 150 mm and outer radius would be 180 mm. Now, to reduce the heat loss to the surroundings and to maintain a safe to touch outer surface temperature, a layer of calcium silicate insulation K of which is 0.1 is applied to the tubes. So the pipe is being wrapped in insulation. Why? To reduce the heat loss and to maintain a safe to touch outer surface temperature. So if someone touches the hot pipe, there is a chance of accident. But if it is wrapped in insulation and someone accidentally touches the insulation, so then it would not be harmful for the worker. So insulation not only reduces the heat loss, but it also maintains a safe to touch outer surface temperature. Now while means along with that, while the degradation of the insulation. Degradation means you would have seen that some of the insulations are fluffy. So if you leave them open, they will just drop off the surface on the ground because they are fluffy. So what is being done in order to reduce the degradation of the insulation? They would be wrapped. So the insulation would be wrapped in a thin sheet of aluminum. The degradation of the insulation is reduced by wrapping it in a thin sheet of aluminum. So as soon as you see the word thin, you should keep in mind that probably the resistance of the aluminum may be neglected. So the degradation, you would have seen you would have seen some thin aluminum sheets. They are even available out there in the market, and we use them in our houses. So those sheets of aluminum, which would be good enough to sustain that insulation, would be wrapped over the insulation, and those sheets of aluminum have an emissivity of 0.2. Now as soon as you are given emissivity, it means that radiation will now come into play. The air and wall temperatures means the air temperature is being given due to convection, and you should keep in mind that the wall temperature is being given for radiation, right? The air and wall temperatures of the power plant are 27 degrees Celsius. So T infinity or T walls and T walls both are 27 degrees Celsius. So over here you can see that the inner radius of the steel pipe is 150, whereas outer radius becomes 180 since it has a wall thickness of 30. And then it is being wrapped in insulation, K of which is 0.1. And then in order to reduce the degradation of the insulation, it is being wrapped in a thin sheet of aluminum. So this is a thin sheet of aluminum having emissivity of 0.2. The ambient air is at 27 degrees Celsius, T infinity outside, and T surrounding means T walls is 27 degrees Celsius as well. Inside this pipe is steam at a temperature of T infinity I of 575 degrees Celsius, and the thermal conductivity of steel wall is 35 watts per meter Kelvin. Now assuming that the inner surface temperature of the steel tube corresponds to that of the steam. Inner surface temperature of the steel tube corresponds to that of the steam. What does this mean? It means that the inner surface temperature of the steel pipe may be taken the same as the temperature of the steam, means 575 degrees Celsius. Now what is happening between the steam and the inner surface of the steel pipe? Convection, associated with which would be convection would be convective resistance, which would be given as 1 over HA or 1 over HIA. So what we can imagine is that though that value of HI would be very large, or that HIA would be a very large quantity, so that 1 over HIA is being negligible. And how do we know it is negligible? Because we are being told that the temperature of the inner surface of the steel pipe may be taken as the same as the temperature of the steam. So if the temperatures at the two nodes are the same, it means that the convective resistance between them is being neglected. Now assuming that the inner surface of the steel tube corresponds to that of the steam and the convection coefficient outside the aluminum sheet is 6. Convection coefficient outside the aluminum sheet is 6. So this is the the convection will take place between the outer surface of the aluminum and the surrounding air, and the radiation will take place between the outer surface of the aluminum and the surrounding walls. So if those conditions persist, what is the minimum insulation thickness? What is the thickness of the insulation? Means R3 minus R2. R3 minus R2. What is the minimum insulation thickness needed to ensure that the temperature of the aluminum does not exceed 50? See, what does it say? We need to find out the insulation thickness, means R3 minus R2. Needed to ensure that the temperature of the aluminum does not exceed 50. This is an important sentence. So we are being told that the temperature of whole aluminum is 50. Now how can the temperature of the whole thing be the same? It can only happen if it offers negligible resistance. So see, what would be the resistance offered by aluminum? Log of R naught over Ri divided by 2 pi KL of aluminum. So what is happening is that the outer radius of aluminum over inner radius of aluminum would be approximately 1. What is the inner radius of aluminum? It is R3. Inner radius of aluminum is R3, which is the outer radius of insulation. And what would be the outer radius of aluminum? You can call it R4, but R4 would approximately be equal to R3, because you probably would have seen those sheets. They are very thin, right? So numerator is very small, because log of 1 point something would approximately be 0, divided by 2 pi KL. So what is the conductivity of aluminum? Aluminum is highly conductive. So a very small numerator and a very large denominator would result in negligible resistance. So the resistance of aluminum will be neglected. So along with the insulation thickness, we need to find out the heat loss per meter of the tube length. Means we need to find out Q by L. Now if we take a look at the thermal resistance network, see, this A is in fact the pipe, tube material itself, pipe material or tube material, pipe material or tube material. And then we have this B. B is the insulation. B is the insulation. And then C is the aluminum. So, and inside is steam, which will offer convective resistance 1 over HA, and outside is air and walls. So see, the resistance, conductive resistance offered by the pipe material, tube material, would be log of R2 over R1 divided by 2 pi K of steel times L. Similarly, the resistance offered by the insulation would be the same, log of outer radius. Now outer radius for insulation is R3 and inner radius for insulation is R2, which is the outer radius of the pipe, divided by 2 pi KL. K would be the K of insulation. And then for aluminum it would be the similar thing, log of outer radius. Sorry, I should have written R4 in here and R3 in here. It would be log of R4 over R3. Log of R4 over R3 divided by 2 pi KL. K would be the K of aluminum. Now R4 is approximately the same as R3. Aluminum is not this thick, it is very thin. So therefore R4 over R3 would approximately be 1.0 something, log of which would be very small quantity, and K of aluminum is very large, so therefore denominator would be large. So therefore small numerator and large denominator would lead us to neglecting this insulation, neglecting this resistance. And since those two temperatures are the same, the inner surface temperature of the steel pipe is approximately the same as the steam temperature, means T infinity I. So therefore this resistance will also be neglected. So out of these four we would have two resistances only, one due to the pipe and one due to the insulation. Now what is happening on the other side? Convection and radiation would be taking place simultaneously, so therefore these two resistances would there be in parallel. The conductive and convective resistances would appear in parallel. So our resistance network would not be having this one as well, and it would not be having this one as well. Right? So now we have to find out two things. One, the insulation thickness R3, and the second thing is Q by L. So if we write Q as Q convective plus Q radiative, what does this mean? Whatever heat reaches the outer surface of the insulation or aluminum. So from the outer surface of the aluminum, the heat will be transferred via convection and radiation simultaneously. Right? So Q would be Q convective, the sum of Q convective and Q radiative. How will we write Q convective? HA delta T. And how do we write Q radiative? Sigma epsilon A Ts4 minus T surrounding 4 or T walls 4. Now how can we write Q? Q would be written as T1 minus T3 over the sum of these two resistances, one due to the steel pipe and one due to the insulation. So these are the two resistances that will come into the denominator. Now area through which the convection is taking place is the same area through which the radiation is taking place, which is 2 pi RL, and R would in fact be R4, but it would be taken as R3. Why? Because R4 and R3 are approximately the same, because aluminum sheet is thin. So over here we would also have 2 pi R3L. Now if we put the values, we know T1 as 575, we know T3 as 50, T3 is 50, right? T3 and TS4 are both 50. Over log of outer radius, R2 for steel is 180 millimeters and the inner radius of steel pipe is 150 millimeters. For insulation, inner radius is 180 millimeters and outer radius is unknown. This is what we need to find out. On the right hand side, we know all the parameters except R3. We know H as 6. We know Ts, temperature of the surface of the aluminum is 50 minus T infinity, which is 27. Similarly, Ts for the surface of aluminum is over here. Kindly note that it is radiation and it is not delta T, it is Ts4 minus T surrounding 4. So we are bound to keep the temperatures in Kelvin. And the temperature of the surrounding walls is 327 degrees Celsius. So the only unknown in this lengthy expression is R3. So if you solve it using trial and error method, of course you will put R3 greater than 180. You will put R3 greater than 180. For example, you may start with 0.2 or 0.25 and then 0.3, right? And then 0.35. So after 2 or 3 iterations you will get R3 as 0.394 meters. Means you will put different values of R3 in here, and then that value of R3 would be considered as the right one, for which the left hand side and the right hand side yield the same answers. So therefore the thickness of insulation would be R3 minus R2. R2 means 0.394 minus 180 millimeters means 214 millimeters. Now how do we find out Q? You can very easily find out Q. All you need to do is put this R3 either in the right hand side of the equation or in the left hand side of the equation, and then you will be able to find out Q by L, because we are not given the length. So you can do it yourself very easily. But now let's discuss about an alternate solution, but it is the same solution. And what do I mean by alternate solution? See, someone may question that we wrote the left hand side as delta T over resistance. However, we wrote the right hand side not in terms of delta T over resistance. So why are we not following the same thing? Means why can't we write the right hand side using delta T over resistance? See, over here in this alternate solution, I am going to write the right hand side in the same manner, means delta T over resistance. So how I would write it then? See, this resistance and this resistance, these two resistances do not exist anymore. So it is T4 or rather T3, where convection and radiation are taking place simultaneously. So T3 minus 27 over resistance would be the right hand side, and then we can write it as 1 over resistance. That would not make any difference. Now 1 over resistance, 1 over equivalent resistance, we have to find out the equivalent resistance of these two resistances which are connected in parallel. So if the two resistances R1 and R2 are connected in parallel, how do you use to write it? You are used to writing it in the form that 1 over R equivalent is equal to 1 over R1 plus 1 over R2, and we have written it in the same form, that 1 over equivalent resistance is 1 over convective resistance plus 1 over radiative resistance. Now T3 minus 27 may be multiplied with both of these terms, so it would become T3 minus 27 over R convective and then T3 minus 27 over R radiative. Now since it is convective term, this 27 can be written as T infinity, and since this is the radiative term, this 27 can be written as T surrounding walls. So now it would be T3 minus T infinity over convective resistance is 1 over HA, and this T3 minus T surrounding, the second term can be written as T3 minus T surrounding over R radiative. R radiative is 1 over HRA. So this HA will go into the numerator and it will become HA times T3 minus T infinity, and this HRA will also go into the numerator and it will be written as HRA T3 minus T surrounding. This HA T3 minus T infinity will remain the same, and if we write HR over here, which we have discussed in week 1, so then it would become sigma epsilon A T34 minus T surrounding 4, which is the same expression that we had written over here. So even if you write it in this form, or if you proceed in this manner by writing both the left hand side and the right hand side as delta T over resistance, you will reach to the same point. From here we are reaching to the same point, so it does not matter.